Welcome to this explainer. Now, when you hear the word doping, your mind probably jumps straight to a headline about, a stripped Olympic medal, a disgraced cyclist, or some clandestine underground laboratory. It's a highly stigmatized word. But today, we are going to completely shatter that preconception. We're going to take this heavily loaded term and just strip it right down to its fascinating foundational science.
Okay, let's dive into this by asking a question that might honestly seem like a riddle at first. What do an Olympic endurance runner and the computer chip inside the very device you're using right now have in common? Seriously, think about it. On one hand, you've got the absolute limit of human sweat, muscle, and biological endurance. And on the other, you have a cold, inanimate piece of rock. The answer here isn't just a clever metaphor, it is literally the exact same scientific principle at work. To understand how one single concept can both break the rules of human biology and build the entire modern digital world, well, we need to redefine what this word actually means.
Section 1. The definition of doping, core science.
Before we talk about biology or inorganic materials, we have to establish the core science. At its absolute core, doping is simply the act of introducing specific impurities in incredibly minuscule and highly controlled quantities to alter a system's natural baseline state. Think about why we'd even do this. A natural baseline just isn't always optimal for what we want to achieve. Nature didn't optimize human blood for racing a bicycle up a mountain at unnatural speeds, right? And nature certainly didn't optimize silicon for streaming high-definition video. You take a pure system and you intentionally add a tiny impurity to change how that system naturally behaves. Keep this definition locked in your mind because it is the master key that unlocks both halves of our explainer today.
Section 2. Doping in sports, human biology.
So let's apply this concept to human biology. In endurance sports, think cycling, distance running, cross-country skiing, oxygen delivery is the ultimate limiting factor. The more red blood cells you have, the more oxygen your body can deliver to your working muscles, which pumps up your VO2 max and significantly delays fatigue. Athletes seek to alter their natural biological baseline through blood doping, and they primarily use 3 methods to do it. First up, autologous transfusion. This is a total logistical nightmare, where an athlete draws their own blood weeks before an event, hides it in secret refrigerators, and then reinfuses it right before competition. Because it's their own blood, it's incredibly hard to detect. Second is homologous transfusion, which uses a compatible donor's blood. And third is the injection of erythropoietin, or EPO. This is a synthetic version of a hormone that's actually naturally produced by your kidneys. By injecting it, athletes basically trick their kidneys into artificially manufacturing a massive surplus of extra red blood cells. All 3 methods introduce a specific variable, an impurity to the natural baseline, to force the human machine to run longer and harder than it ever organically could. Now, because these methods manipulate blood volume and composition, you might be wondering about the anti-doping testing process itself. Well, to put things in perspective, a human body holds roughly 200 to 400 tablespoons of blood, depending on size and sex. When anti-doping agencies draw blood for testing, they take less than 2 tablespoons. I really want to emphasize this because there's this persistent misconception out there that testing itself drains an athlete. Drawing such a microscopic fraction has absolutely zero effect on athletic performance, but it provides the critical, highly precise data needed to maintain a level playing field against these biological manipulations.
Section 3. Catching cheaters, detection strategies.
But as athletes found new Dizymer drugs and more sophisticated transfusion methods, anti-doping agencies had to drastically evolve their detection strategies. And this brilliantly illustrates the shift in the science. Traditional drug testing was a direct approach. It involved looking for a snapshot in time to find the direct presence of a prohibited substance or its metabolites. But with the onset of rapidly modified designer drugs, the snapshot just wasn't enough anymore. Why? Because these new drugs are engineered to leave the system incredibly quickly, or their molecular structure is tweaked just enough to evade traditional tests. If you test an athlete on Tuesday, the drug might be entirely gone by Wednesday, even though the massive performance benefit remains. Anti-doping agencies needed a new strategy. Enter the athlete biological passport. Instead of looking for a static snapshot of a drug, the passport essentially creates a continuous video of the athlete's biochemistry over time.
The Athlete Biological Passport, or ABP, uses advanced statistical tools to generate longitudinal profiles. It monitors an athlete's internal biomarkers over their entire career. For the blood module, this means tracking hemoglobin, hematocrit, and red blood cell counts. It establishes a highly personalized reference range for that specific individual. This is absolutely crucial. It draws a custom boundary line for every single athlete.
An athlete can no longer hide their manipulated data within the generic population-wide averages of the sport. If an athlete's data suddenly spikes and falls completely outside of their own natural historical limits, boom, it flags the system. It's an indirect method of detection. Even if the authorities can't find the specific designer drug, the unnatural fluctuation in the body's baseline proves beyond a doubt that an impurity was introduced. The system caught the effect of the doping, even without catching the drug itself.
Section 4. Doping in electronics, inorganic materials.
Now prepare for a hard narrative pivot. We've talked about manipulating biology, but that exact same scientific concept, introducing impurities to alter a baseline, is the reason you are able to watch this explainer right now. Without doping, modern technology wouldn't exist. Introducing impurities into chemical elements is literally the foundational engineering step used to build the entirety of the modern digital world. Now, what's really interesting about this is that silicon, the famous material that built Silicon Valley, is practically useless to us in its native, pure state. Undoped silicon is a poor conductor of electricity. Sure, it has some natural conductivity from broken covalent bonds in its crystal lattice, but it completely lacks useful variability. Think about it. To do computation, to process the binary ones and zeros of digital code, engineers need to turn electrical currents on and off with absolute rapid-fire precision. Pure silicon simply doesn't give us that control. To make silicon useful, we have to actively control its properties. We have to dope it.
Section 5. P-type versus N-type, semiconductor doping.
By introducing trace amounts of chemical impurities, or dopants, engineers can transform this pure intrinsic semiconductor into an extrinsic semiconductor. Let's slow down and look at the chemistry here for a second. If we look at the periodic table, silicon sits in group V. It has 4 valence electrons. To change how it conducts electricity, we can mix it with elements from neighboring groups. Think of it like a massive game of musical chairs. If we dope silicon with a group V element, like phosphorus or arsenic, those atoms bring 5 valence electrons to the party. 4 bond with the silicon, leaving 1 extra, free-roaming electron with no chair to sit in. Conversely, if we dope silicon with a group 3 element, like boron or gallium, they only bring 3 valence electrons. This leaves a missing bond, an empty chair known as a hole. Even though it's an empty space, this hole acts as a positive charge carrier, because other electrons just keep moving into it. So the crucial point is how these two types contrast. When we add group 5 dopants, we create an N-type semiconductor. N stands for negative because we flooded the material with extra negatively charged electrons. When we add group 3 dopants, we create a P-type semiconductor. P stands for positive because we've introduced these positive holes that allow charge to flow. By carefully controlling these impurities, engineers completely dictate how electricity moves through the material. It gives us total, absolute control over the current. And the technology for doing this is becoming astonishingly precise. Traditional thermal diffusion or high-energy ion implantation could be, well, kind of messy, sometimes causing crystal damage or non-uniform dopant profiles. But today, the semiconductor industry uses techniques like atomic layer doping, or ALD. ALD offers unparalleled control, allowing engineers to place dopants almost atom by atom. To understand the scale here, we are talking about engineering at the absolute microscopic level. This precision minimizes crystal damage, can actually increase electron mobility by an incredible 50%, and reduces leakage current by 10 times. This absolute mastery over impurities is what prevents our powerful smartphones from instantly overheating in our pockets, and it's exactly what allows our computer chips to get smaller, faster, and way more efficient every single year. Let's move to how this builds into the devices we use every day. If you take a piece of P-type silicon and seamlessly join it to a piece of N-type silicon, you create a heterojunction, specifically a P-N junction. This interface is the magic barrier. It acts as a one-way turnstile for electricity, allowing current to flow in only one direction. This single, simple structure is a diode. If you sandwich 3 layers together, you get a transistor, the microscopic on-off switches that make up the processors in our phones, computers, and even the photovoltaic solar cells powering our grids. None of it happens without doping.
Section 6. The final thought. Impurities in science.
As we wrap up this explainer, let's take a moment to reflect on what we've unpacked today. We've taken a word usually reserved for scandal and viewed it entirely through the lens of pure science. The exact same scientific mechanism, introducing impurities to alter a natural baseline, fuels the darkest controversies in Olympic sports and serves as the brilliant foundation of all modern electronics.
It's a powerful reminder of how neutral scientific concepts are ultimately shaped by human application. So I'll leave you with this provocative thought. As our technology and our understanding of human biology grow exponentially more advanced, how will we continue to use the science of impurities to manipulate both our bodies and our environment in the future? Thank you so much for exploring with me today.